Okay, welcome everyone. So I'm going to tell you what I did this summer, okay, with Yonju, who was a Z1's intern, Mark Selke, and Yintat. Okay, so the story begins like this. So we're going to talk about selection problem. So what is a selection problem? So let's say you have a family of sets. So this is a family of sets, script K. And what you want is to select a representative element for each set in that family of sets. Okay, so a selector is a map S from K to the background set. Okay, so each set are element in X, such that for any set in K, you have that S of K is in K. Okay, so this is a selector. Just for every set, you have to choose a representative element. Okay, so this type of problem is extremely general. As you can imagine, I mean, you know, when you start talking about set and just choosing elements in set, you can model anything like this. So famous questions around this are like the axiom of choice, you know, whether such a selector exists when you have an infinite family. But there are also much more practical questions like measurable selection. So, you know, as soon as you start to have a structure on the set X, you can ask, does there exist a selector which has some nice properties? Is it going to be continuous? Is it going to be measurable? Is it going to be Lipschitz? And all of those things have been studied, and they are important, for instance, to show existence of solutions to PDEs and things like that. And we use the measurable selection theorem in our work on K-server, you know, to show that mirror descent.
Measurable selection theorem, right?
Yes, okay. Absolutely. Yeah. So all of this is great, and what I'm going to tell you about today is online selection. Okay, so online selection, it's a much more sophisticated problem where instead of having a map which just takes one single set, it's going to take a sequence of sets. Okay, so the selector will have a memory, and we will want to use this memory to improve some properties. So online selection is just that the map S is now from strings of sets to X, and again such that for any sequence K1 up to KT of sets, you have that when you input this sequence K1 up to KT, you output an element in the last set. Okay, so that's what we're going to care about. And we're going to restrict our attention to the case where the background set X is a metric space. Okay, so you have a notion of distance between elements. So when you have a notion of distance between elements, the most natural question is whether there exists a Lipschitz map. Okay, so a selector, so in this talk, and in our work in general, and in general in online algorithms, it's very natural to assume that X is a metric space. And then the natural question in that case is the following. So a selector is Lipschitz, is let's say L Lipschitz, if the following holds. So now the notion of niceness is going to be a notion of robustness, of stability. Namely, if you input two sets which are just slightly different, which are not too different from each other, then you would like the selector to output two elements which are not too different. Okay, so it's L Lipschitz if the distance between the element that you select on K and the element that you select on K prime, this is smaller than L times some notion of distance between K and K prime. And there is a very natural notion of distance on sets, which is the Hausdorff distance, and I will just remind you what it is. Okay, so this is just a notion of distance that tells you that basically if you have a set and a small perturbation of that set, then this distance should be small. Okay, so again, this is a notion of stability or robustness. Okay, so again, the notion of distance is the following. You can think of it as, I'm going to show you K, think of it as a request that you have to satisfy, and then I'm going to show you K prime. The distance that you travel is the cost that you pay. Okay? Now, what I'm going to do is that in the Hausdorff distance, I'm going to look at the worst starting point. So from the worst starting point in K, how much distance do I need to travel to satisfy K prime? Okay, so this is equal to the maximum over x in K of the minimum over x prime in K prime of the distance between x and x prime. So I want you to think of this as opt. If I knew in advance that I'm going to get K and then K prime, okay, this is the best I can do if I was starting from the worst starting point. But of course, my selector doesn't know which set it's going to see. So it has to plan for every possibilities. Okay, so in an online state of mind, you should think that this is, you know, what the online algorithm is paying because it doesn't know what it's going to be presented with, and it's compared with the optimal thing it could do.
Distance, right?
Very good. So this is asymmetric. So to make it symmetric, I will take the max between this and the other quantity, which is max over x prime and k prime, mean over x in k, and the distance between them. Okay?
Will this symmetry be automatically certified with some kind of L2 distance?
Good. So the symmetry is not going to be important for us in a second. The symmetry is important in this offline case, in this classical scenario. But for online, there won't be any symmetry. I mean, things will be presented like there will really be an order. Like it will be k, and then k prime, and then some k double prime. Okay. All right. So, yeah.
Did you say this is the optimal?
Because this is the optimal from the worst starting point.
If you play for 2 rounds?
Yeah, of course, if you play for 2 rounds. So this is the classical case. This is just L Lipschitz. So now, okay, now I'm going to say that your online Lipschitz, so you have an online selector. An online selector is online Lipschitz. So now I think of this as a distance I travel to satisfy k and then satisfy k prime. So now I'm just going to look at how much do I move to satisfy the sequence k1 up to kt. Okay. So online Lipschitz, I look at my cost, the sum for t from 1 to capital T of the distance between. So now I have s of k1 up to kt, and the distance from this to k1 up to kt plus 1. Okay, so this is a distance, the total distance I travel to satisfy all of those requests. And I want this to be comparable to L times opt. And now what is opt? Opt is the smallest distance I could have traveled to satisfy all of these requests from the worst starting point. Okay, so best from worst starting point. And for the expert in online learning and online algorithm, notice that I don't allow some additive constant or anything like that. I don't really, you have to be just smaller than L times opt.
Wait, I'm curious. So for solving this problem, isn't this relation of Hausdorff distance a little bit too pessimistic in some sense? Because you're kind of like locally pessimistic always. So maybe there is some way to kind of prune some outliers and just don't go there, something like this.
Yes, I mean, here's one difficulty is this order on things. I mean, you can imagine, you know, if I show you like a huge ball, you know, and I first tell you, you know, I show you a small ball here and then a huge ball there. I mean, you don't know in the huge ball, it really depends. Are you showing me this or are you showing me that? So, you know, in just this one step, you have to have this maximum between the two orders.
But the opt doesn't, the definition of opt there doesn't have anything, like, it doesn't use the Hausdorff.
No. This is opt is just the minimum over all sequence of points where each point is in each set, but with the worst starting point. Okay, so here are some theorems and conjectures.
So you assume that your like space is bounded or something like this, because then like.
Yeah. Good. No. So what we're gonna
so what does it
look
mean
at?
that worst starting point?
Yes. Okay. So yeah, very good. So here is what I'm gonna do. So imagine the worst starting point. Think of it as this has to be true for any sequence of sets. So indeed, if the first set is all of, say, Rd, if you're doing things in dimension D, then this tells you nothing.
Or, like,
But you can know if you're not happy with this, just think the first set is some point. You start there, and then the worst starting point is the same for everyone. This is just more general than this. Okay, so our focus today, but this is not at all the only interesting thing, is the family of sets that we're going to look at are all convex sets in RD. So K equal all convex sets in RD.
Bounded?
No, just all convex sets. All of them. Okay. And maybe just a word about some applications of this. This has infinite number of applications. So this generalizes, I don't know, metrical task system, K-server falls into this, but it also, specifically in the case of convex set, if you can solve this, you get online learning, you get online convex optimization. So for those who know about online convex optimization, you might think about the fact that here you see first the constraint and then you make a decision, whereas in online learning you make a decision and then you see whether it was a good decision or not. But this is exactly why you have this distance. This distance is exactly the price you pay between the decision now and the decision tomorrow. Okay? So anyway, I won't discuss those things. Also, lots of application in power management. So there are now hundreds of papers on this. You can imagine your set. The simplest case is imagine the set is just like two elements. Either I need my laptop to be on, or I don't care if it's on and off. And you have a price to pay every time. If it's on, then it's consuming some battery. Okay, so this is literally, you can write it as an online problem like this. Okay, but I won't talk about those. I want to tell you how to solve this problem. So here is a folklore theorem. So again, now we only talk about convex sets in RD. And so the first folklore theorem is that there exists a Lipschitz selector in this case. It's not quite obvious, so we're going to talk about this. And the conjecture that we resolved from...
You mean with like arbitrary, like potentially crappy L?
Yeah, potentially crappy L. So in fact, this theorem we know the exact optimal L, like the exact value. Okay, so
it's corollary of your results, it's not folklore.
No. This is folklore, also the exact value. So I'm going to talk a little bit.
Okay, I see. So you are saying that there is a gap. So actually, this is much easier problem than designing this online Lipschitz selector.
Yes.
Okay,
This is much easier.
No, it's easy to solve, but it's harder in that you get bigger L, because it's more like in some sense.
Oh,
stronger.
you mean here?
Yes.
So we don't know. So the conjecture is basically that you can. The conjecture is that basically. There are statements about this. So L is square root D. Okay. And the conjecture is that you can do the same thing in this much stronger sense. You can also get more.
I see. So
So
there is
you are
no
saying
reduction
that
between.
offline we know and online we don't know. That's all you're saying.
Yes.
Okay.
But the conjecture is that online is not harder than offline.
Yeah,
This would be
sure.
an amazing result. So we
Yeah,
don't have that.
okay, so basically this like online Lipschitz selector implies
Yes.
right hand side with the same.
Yeah, of course.
Okay.
If you have this, it implies that. Yeah.
But the other way around?
No, not at all. So if you have this, it's
No,
much.
but online selector.
Sure, yeah.
Like in the sense of line two of your definition.
Yeah. If you have an online selector that satisfies just the classical Lipschitz, you're asking, does it imply online Lipschitz?
Oh, I see. So it's not well defined for the sequence of sets.
No. This is just defined for two sets.
Okay.
So the conjecture from Friedman-Linial, so the paper was published in '93, but all of those conjectures are from the end of the '80s, is that there exists an online Lipschitz selector.
Is this all for convex sets?
Yes. Now we're only talking about convex
And
sets.
distance is L2, right?
Distances doesn't matter in such a statement, right? They are all equivalent,
But think of L2.
but think of L2. And this was open for D equals 3.
For the L, we need for L to be root D, you need L2, right?
Yeah.
Yes.
Okay.
So the general conjecture would be L is D for any norm.
That's true.
Okay, so that's what we proved. So the theorem. So again.
So why did you say that the norm doesn't matter here?
Just because all norms are equivalent, you know, up to.
Oh, you don't care about the root D.
Yeah, you don't care about the root D. So again, yeah, it's myself, Yintat, Yuanji, and Mark. Is that this is true? And
Square root D.
no, no, that would be a really, really strong result. No. So again, here, so the L, the optimal L, is of order square root D. Okay. For classical Lipschitz, and I'm going to talk briefly about this. For online, the conjecture is that, so we know that L has to be at least square root D, just because, of course, it has to be. And the conjecture is that you can get square root D for L2. What we prove here is 2 to the D. Okay, so we prove exponential.
So what is known about these results for like worst case finite metric spaces?
Okay, well, it's open. I mean, that's what we were talking about.
Okay.
Yeah.
Just, yeah.
So it's super natural. I mean, it's really, really natural, but people have not studied it. Yeah, and there is a lot to be said about this.
What does that mean?
So, you know, again, this is very general, this family of sets. Now I'm specializing to the set, all convex sets in RD, but another natural case is if X is just a finite,
Just some arbitrary metric.
some arbitrary finite metric space. What is the dependency on N? So in fact, this is exactly metrical task systems. But then there is the question, the classical question. Okay, so let's do something. Okay, so this was just the background and a tiny bit of motivation. Let's talk for a minute about this folklore theorem. So maybe do you have a suggestion of what would be a selector? So again, I show you a convex set. You have to tell me, select a point in that set. What would be a natural point to select?
I think whoever reads Twitter knows the answer.
Okay, yes. So, okay, a natural thing. So let's just so warm up.
So why is it not like a flow problem?
So again, we're just talking about convex right now, not finite. So a natural selector is just the center of gravity. Center of gravity. Right. I mean, this is something that we'll know and love in optimization, in convex optimization. This is not robust. This is not Lipschitz. Okay. No. And here is the reason. Just in dimension 2, nothing fancy. Imagine that I have a small triangle like this. This is tiny, epsilon. Okay. Where is the center of gravity? Center of gravity is somewhere here. You know, 1/3 from the base. But when I collapse this dimension, center of gravity is going to move to 1/2 on this. So in terms of the set is making a microscopic movement, but the selector is making a macroscopic movement. Okay, so this is not at all robust.
Wait, yeah, but so this is like continuous. I mean, it's a continuous process of moving there, right?
Yeah. It's a continuous process, and then you have this discontinuity.
But I guess the L gets larger.
You see, as epsilon goes to 0, this is just going down.
Yeah.
And then suddenly, poof, it jumps.
And the width stays the same.
Yeah, the width stays the same.
Okay.
So it's really bad. You really don't want, this is really not robust.
It's a bit counterintuitive too.
Yeah?
Are you sure the width stays the same? It seems that for the two-dimensional case, width is at least positive, and then for one dimension, then it's measure 0. So
But the
essentially
Hausdorff
it's nothing.
distance is constant.
Yeah. So the point is indeed that the measure, the Lebesgue measure is just
I see.
not
So
a
it's
good object.
0 versus non-zero measure.
Yeah,
Okay.
it's 0, you're right. I mean,
Yeah,
this
yeah.
is a problem. Richard, you wanted to ask?
So how do you measure? I'm not familiar with like Hausdorff and Lebesgue.
Yeah, that's fine. Yeah.
So for that example, if I half one of the sizes,
Yeah.
the center is that is.
Yeah, but as you go.
So-
if I take the length and I just half it.
Increase.
This one?
Yeah.
Yes.
L.
So
Yes.
how are you measuring the distance? So your distance measure says that if it's like a little bit here and it's 0, these two are close.
Yes.
So can you just explicitly?
So imagine the distance between this set and just that set.
Uh-huh.
This is intuitively whatever distance you want, this should be epsilon. These two sets are epsilon close to each other.
Well, not in terms of measure, for example. So.
But in terms of that,
But- but in terms of
I
distance-
understand. But I think this example shows that the definitions are in some sense wrong.
Yeah.
Well, no, because you can get
No,
something.
I understand, but still.
You could get
yeah.
something for maybe with another definition for center of gravity.
Sure,
yeah,
sure.
that's true.
Yeah.
Yeah.
Can't you just like take some like John's lips or something?
John will not work, but you're on the path to discovering something. Something, if I let you think for one more minute, many of you are going to come up with the idea of taking something very deep inside, meaning that, instead of John, the problem of John is exactly trying to be smart. But you don't want to be smart, so you want to find a point which is as close as possible to its furthest point. So instead of looking at ellipses, you want to look at just ball. Okay, so this is the key thing is that this is a affine invariant, and that's not good. You don't want to have something that respects the ellipse geometry, because between this and this is going to be very different. So what you want is just to look for a ball. So this is the Chebyshev center. So again, the Chebyshev center is the point such that my set is contained in the. So for any point, I can look at the smallest ball that contains my set, and I'm trying to find the point which has the smallest such radius.
So it's like minimum circumscribed.
Yes.
Pretty much.
Yes, exactly. So Chebyshev center will be robust, but in fact, amazingly, mathematicians are pretty good.
It can
Yeah.
be outside of this. So it's among only points in the set.
Among
so
points
it's
in the
not
set,
minimum,
yes.
minimum.
It's among points in the
Okay,
set,
okay,
yes.
okay.
So we know the exact answer to this question, and the exact answer is what's called the Steiner point. So the Steiner point, it's very beautiful, related to things that we like in optimization, Frank Wolf and conditional gradient. So the formula is like this. You remember the support function of a set. This is just the maximum of the inner product x dot theta for x in k. Right, so I just choose a direction and I look at the maximal value. So you know that the gradient of the support function is just the argmax of the same thing. Right? So the gradient of the support function is just I pick a direction and I look at the point which is the furthest in that direction. So the Steiner point of a set K is just I take a random direction, and then I look how far can I go in that direction, and I just average all of those answers. So I just take the expectation of the gradient of hk at theta. This is quite a beautiful formula. Okay, does that make sense? So if you want, it's doing an averaging of the vertices of the polytope, but with a measure which is not the uniform measure. I'm not taking a random.
Not just vertices, the whole boundary, right?
Yeah, but think of a polytope just to simplify. I mean, it is.
Sure.
If you define vertices as extremal points, then this was correct. And so this is called also the curvature centroid, because you can think of it like this. I have a polytope, let's say, and here I have a cone, like this dual cone here, which is just like 90 degree here, 90 degree here, like the same thing here. Okay. And these cones, they make a decomposition of the sphere. Okay, so the whole sphere is going to be decomposed in those cones. And what happens is when I take a direction, if the direction falls into that cone, then it means the answer is going to be that point. That's exactly what it means. And what I'm doing is that I'm assigning mass to the vertices of the polytope, which is proportional to the measure of that cone. Okay,
Like
so
the angle.
the angle. So this is exactly, the curvature. If it was continuous, it would be the Gaussian curvature. Okay, so as an exercise, you can check if you're interested. You can just do an integration by part on this formula. You will get some other formula. If you're in online learning, this is just the 1-point bandit estimation of the gradient. And from this other formula, it's very easy to prove that it's Lipschitz. Okay, and the fact that it is the most Lipschitz is just crazy beautiful. So the way you do it is you start with any selector, and then you show that from any selector you can always symmetrize it. You can make it respect a certain set of symmetries, and that will only make it more Lipschitz. And then you show that there exists a unique symmetric selector, which is Steiner. So that tells you that Steiner is just the best.
Like, which symmetries are you like?
For instance, that it's additive with respect to Minkowski. S of k plus k prime is equal to S of k plus S of k prime. Yeah, this is a crazy beautiful proof.
That's your proof, though, right?
No, I wish. I wish. No. This is from mathematicians in the 70s.
So then why did you mention the Chebyshev center?
Because Chebyshev center is also Lipschitz. It's not the most Lipschitz, but it is Lipschitz.
Oh.
And also the square root d or worse?
I think so. I think also it's
Just worse constant.
Yeah, just worse constant.
So is root d a constant up to constants, or is it just root d literally?
No. It's up to constant, but there is an exact formula that you can derive.
Okay.
Which is, yeah.
And that's constant, like, exactly.
And that
Sorry,
constant
that's-
is exact just because, in fact, you don't show that square root d is the best. What you show is Steiner is the
In any
best.
dimension.
In any dimension.
So something I'm getting confused because especially if you're specifying this as a set of convex bodies, you can actually compute this optimal selector. I'm confused, like why this is just an algorithmic problem, right? You're
Infinite dimensional though. I mean, you're optimizing over, you're optimizing over all maps from all convex sets. This is a big space. It is, if you want, you can think of it as a, what?
It's like the space
it's
of
like-
convex functions is called.
It is convex, indeed, it is a convex set because if you have two selectors, any convex combination of them is still a selector. That's a good point. That's true. That's true.
Oh, that's why.
I don't know if
there
that-
exists a unique optimal.
That's a pretty good point.
I mean, at
Convexity doesn't
least
imply.
if you
What?
Convexity doesn't immediately imply it's unique. Or
No, it doesn't. But
it.
still, maybe it's an interesting direction. Yeah, I like this. Okay, so now I'm gonna. So this was all background. Now I'm gonna tell you how to solve this problem. Okay, so I'm gonna tell you a new algorithm, which does something, I think.
By the way, Paul, face these results about Steiner point?
What? This one?
Yes.
Lots of people. So the thing is, the literature is pretty unclear. So there is a book by Greenbaum, the famous book on convex set from the 60s. So he talks at length about Steiner point. He doesn't prove, so at that time they didn't know that it was the unique symmetric selector. So that was proved later by Ost and a Polish name which is just too complicated for me to remember. Beginning of the 80s, and also the bound, even the upper bound, it's very simple, but the upper bound does not appear in the literature until 85. But a lot of this is hidden, at that time in math, many people were running those seminars and they weren't publishing papers, they were just, not publishing, they had compte rendu, du séminaire, like what Grothendieck was doing. And so that's what they were doing.
Like Grothendieck.
But if you just wanted like theta root d, there's pretty simple proofs, right?
So I am looking right now for a proof of this lower bound, like a computer science proof, not a nice proof. And I don't have one.
Maybe what about the upper bound?
No, I mean, the thing is, right now the proof is just so perfect, You're not showing that it's square root d, you're showing Steiner is just the best. So whatever you get for Steiner, that's the right answer. I would really like to understand if there is a more hands-on version of this proof. And this I don't know how to do.
So why was Steiner point introduced in the first place?
Excellent question. So it was introduced in 1840, and it was to solve a problem published in 1817. So that's where the 1817 comes from. So this was some extremal combinatorial problem, of geometry in the plane. And then Steiner introduced this point as a curvature centroid to show some inequalities on triangles. And then, there is a huge literature on this. It's really... Problem is, none of this is useful for our problem. Okay, so that's a little bit of a bummer. So what we do is different. Okay. So what we do in a, if I wanted to say it in one sentence, it's like a multi-scale ellipsoid method. Okay. And many of us have used this, so I use this with Ronan to solve the information theoretic convex bandit. Yuanju used that with Elad to get his exponential in the dimension algorithm for the convex bandit. I don't know if we used it with Hintat at some other point, but anyway, this general idea of doing a multiscale ellipsoid is very useful, and not many people have gotten it yet, so there are still more things that we can do with. So it works like this. So high-level strategy. So as we pointed out, we're not making any boundedness assumption. The space could be huge, or things could happen in a very tiny space. So what we're going to do is that we're going to have a phase-based strategy. Okay, so phase-based. And during a phase, we're kind of localized. Okay, we say that the theater for what's happening is right there. Okay, so this is some ball. It's centered somewhere. So there is some center Z and some radius capital R. Okay, so we localize. So localization set is some ball centered at Z and of radius capital R. Okay, and a phase is really selected with two things, a center, Z, and a scale, which I'm going to denote little r. Okay, and this capital R is just going to be some multiple of little r. Okay, think of it as like d to the 100 times little r. So little r is a scale that we currently care about, and capital R is where we're going to look at things. And what's going to happen? We're going to get a set. Maybe this is K1. Okay, we get a first set. Then maybe we get a second set. This is maybe K2. Okay, we get a third set, maybe like this, K3. Okay, we keep getting sets like that. And what we're going to keep track of, the key idea is that we're going to keep track of what the optimum could be doing right now if it was not moving very much. If the optimum already is moving a lot to satisfy those requests, then it doesn't matter what we do. The only tricky part is if opt is not moving and we are moving like crazy. Okay, so idea, keep track of a low cost optimum. Okay, so what I'm going to say is where could be opt if it was paying less than the current scale and it was staying in our localization ball. Okay, so where can be opt if, one, it pays less than little r, and two, it stays in our localization ball. Okay, so one thing we definitely know is that if it's paying less than little r, it has to stay at distance little r from all of the constraints. Okay, so I can just inflate my constraints like this, a little bit, like that. And I know now that you have to be in the intersection. If opt is staying in BZR, BZ capital R, and it's moving less than little r, then it has to be in this set. It cannot be anywhere else. Okay, so let me denote by omega the tracking set.
Wait, you mean pays at most are for all the steps that we've already observed? Or?
In that phase, yes. For all the steps in that phase. So in fact, we know more than this. This is like level 0 of what we know about opt. But we could look at the whole sequence and say more intelligent things, and we'll have to do that. So omega is a tracking set, so 0th order version is simply that omega is the intersection of our localization ball intersected with the intersection of all the requests k that we have seen in this phase, k requests in the phase, of k inflated by little r. Okay, B is a Euclidean ball. So I just inflate all my sets a little bit, and I intersect all of them, and I know opt has to be in there. And what I'm going to do is that I'm going to wait for this set to become small. And if it becomes small at some point, so I'm going to engineer it so that it becomes small at some point. And if it becomes small at some point, then it means that I can zoom in. I can zoom in on this location. So there will be two possibilities. Either it gets small somewhere here, somewhere inside the ball, and then I know I can zoom in. Or it becomes small over here, but then it means that opt could have escaped, and then I grow the ball. So this is.
Wait, what if it doesn't become small?
So, as I said, I will engineer what we do so that it has to become small. Just think of it like...
I don't understand. The definition of the set doesn't depend on your decisions at all, right?
It does, because just think that the request is like always... I'm always seeing a request where I'm not in. Right now, I'm sitting somewhere, and I'm getting a set that does not contain this point. So think of it like maybe I'm sitting at the center of gravity of this.
I see. Okay. So basically, if you are screwed, then it will have to shrink.
Yes. If you're screwed, then it will have to shrink. And again, this is exactly the ideas that Yuanju used with Elad and that I used with Ronen and Yintat in the second paper of the restart for convex bandit. It's the same, exactly the same thing. But basically, so either you zoom in and you reduce uncertainty, or the uncertainty has gone up. But if the uncertainty has gone up, then opt had to pay for it. So now you're going to analyze this through a potential argument. So I will just write the potential, but and not do the proof. But the proof is 3 lines. So it's just about finding the right potential. But once you have it, it's very simple. Okay, so the potential analysis. Okay, but maybe again I say so. We have two things that can happen. So wait until omega is included in some small ball, b, y, let's say capital R over 10 for some y. Okay, and as Ilya said, it's not obvious that such a time will come, but let's say we reach a time where the set has shrunk, okay? Instead of being of size capital R, it's of size capital R over 10. Then there are two options. One is omega does not intersect, let's say, yeah, it just does not intersect BZ, what do I want? Yeah, maybe like this, minus BZ, R minus little r. Okay, so I'm just saying it's not in this annulus. So you have a very tiny annulus here of protection, if you want, here, like this. If my set, so right now my set is this. So if my set, when it becomes small, it does not, basically it does not live close to the boundary. If it's not reaching the boundary, then shrink.
This includes a case where it becomes empty?
Excellent. So the case where it becomes empty is non-trivial. So you do something a little bit different when it becomes empty. Maybe let me come back to it. Okay, but indeed the case where it becomes empty is just slightly different. Okay. But let's say right now things do not become empty, because if you want, just think if things become empty, that means that opt couldn't satisfy. So we're good. Okay, so shrink. So what does it mean? So shrink just means that in Z I'm going to put y, and in little r I'm going to put little r over 2. Okay, so I just shrink my scale and I refocus over there. And 2 is otherwise grow.
Do you also decrease big R?
Yeah, big R is just, think of it as d to the 100 times little r.
Do you change it at that step at all?
Yeah, you change it.
I see. Okay.
Yeah. You always keep like d to the 100 times little r. And otherwise you grow. Okay, so when you grow, z remains z, but r gets multiplied by 2. Okay, so you think of it as like an accordion. It's going to move like this through space, the selector, the way it's doing it. Okay. And the potential analysis. So I will just write the potential. Potential analysis is a thing that we always do in online algorithms, which is the distance to opt. So the norm of z minus o. So this is opt location. I know if you've heard other talks from me on MTS or K-server, difficulty is always to think about what opt is doing, right? This is always, you don't know because opt is making decisions based on the future for some strange reason. So you need to account in your potential the fact that maybe opt is moving for reasons that completely escape you right now. Okay, but if it does that, then it's going to bring the potential up, and this high potential will let you make progress, in the future. So that's the idea. So this is the potential that we always use. But if anyone has looked at these chasing convex bodies or this type of problems, there is always a big issue with this type of potential. It's great, but imagine the situation is like this. Opt is very, very far, super, super far. And I make a little movement like this. Okay, so this is me. I'm moving towards opt. I'm very happy. But because L2 is not nice, in that case, L2 becomes quadratic here, you see? Because I'm like moving on a sphere. So what happens is that if this is epsilon, then my distance to opt has improved by epsilon square. Okay, and this is a huge issue, this epsilon square. This, once you realize this, by the way, you can solve other problems, because that means that if you were measuring opt with respect to the norm squared, then in fact things would be very easy. So in my definition, if I measure my movement with just the norm, the Euclidean norm, but I measure opt with the Euclidean norm squared, then I can get very easy online algorithm. And in turn, what this implies, for instance, it implies for bandits that you can get these bounds that depends on the sum of the movement of opt squared. Okay, so in bandit, in linear bandit, for instance. So I won't talk more about this, but there is a use for just this observation. But in our case, what we're going to do in this case is that if opt is very far, then we're going to improve. What's going to happen is if opt is very far, we're going to grow. Okay, so what we will say is that we do minus r over 10. And this minus r over 10 is the thing that's going to improve when opt is very far. And then we need another situation, which is when opt is very close to us. Maybe opt was here. This is opt. And maybe now we are refocusing, we're resuming like this. We're moving here. You see, so we are moving away from opt, but we're still winning something, which is that we're shrinking. So what we do is we take, and this is a case where this is small, so we're just going to take the max between this and r over 10. Okay, this is a formula that I like quite a bit. And once you have this formula, and you just put in equation the words that I said, you get the following claim. The change in this potential plus the movement of opt, the change in opt, in a phase. This is lower bounded by some small constant that depends on the dimension, something small, times r. Okay, so again, what does it mean? It means that you have certified at the end of a phase, either you have improved your potential or opt has paid. One of the two has happened. So at this point, the only thing that's left to do is, can you show that your algorithm, the movement that your algorithm is making is smaller than some constant times r. Okay, so if you manage to show that in a phase you can engineer your movement so that you ensure that things shrink at the end, and you don't move too much to induce this shrinking, then you're done. Okay, so it's all about how do you move to ensure this shrinking. And I already gave away part of the answer, which is very naturally sit at the center of gravity. Okay, so let me... Of omega. So I will conclude with this, so this should be less than 10 minutes. Okay, so is the high-level strategy clear? So this was, if you want, this is like the skeleton of the algorithm. Right now, I didn't tell you what is the algorithm. I didn't tell you how, you get a request, where do you go? I didn't tell you that. I just told you that if the algorithm satisfies something, which is it doesn't move too much until it ensures that the omega set, the set where opt can be, has shrunk, then you're good. Okay. So the strategy.
Can I ask a random question?
Please.
Related to the problem, but not to what you're explaining. What if
Yes.
all our sets are balls? Does it make the problem easier?
Yes. Yeah. So no.
Not really, actually. Half spaces are already hard.
Right. So what happens is that if the ball can be of infinite radius, then it's like a half space, and any convex set you can present it as a bunch of half spaces. So instead of showing you this. I'm going to show you first that. Then I'm going to show you this.
Yeah, but it gives us more flexibility because we don't need to be inside the set proper, right? Like as soon as we...
No, but you know, if you have an algorithm that satisfies this, you can also make it to satisfy just the triangle.
Okay.
Yeah. So.
Actually, yeah, this is actually very general.
Yes. Yes.
No, but it's not entirely obvious, so it is obvious.
No, it is obvious. So.
So any
all the
convex
convex sets are false.
So you see, just.
No, I mean approximating any convex set with half space is sure, but then like why can't my algorithm?
You can think, you know, you were.
Like what? My algorithm doesn't have to be in this intersection.
It doesn't have to be in the intersection, but let's say it was here, and then it has to move there.
Oh, okay. We just okay.
Yes.
Yeah.
It was better to move there. You can think it was better in the first place to move
Okay.
there.
Okay.
Yeah. Okay, good.
Like ask like, let's say like for the triangle, I can just ask like first condition, second condition, first condition. I can just ask those three conditions repeatedly.
Okay. Sure.
Yes.
At which point you must basically.
Yeah, exactly. Yeah. Yes, exactly. Yeah, you're totally right. Good. By the way, there were papers like doing literally, what if your shape is a single triangle moving? You know, and already that is not so easy, but okay. So, how to move in a phase? So the basic idea would be go to CG of omega, center of gravity.
So one question.
Yeah.
So this potential should be bounded by something. So what is this?
No, you can just show that it's always bounded by the value of opt.
You're okay.
Yeah.
That's not clear from that.
It is because you can just say, you know, you can keep track. I mean, this is bounded by the norm of Z plus the norm of O.
Z is your.
Z is your center, and you know you can do it by induction.
Yeah, nice.
Yeah. Okay, so if you go to the CG of omega, then what happens? So this is your omega right now, and you're in the center of gravity. And now what you can assume is that you're going to get a set which does not contain K. Okay, so this is K. It does not contain the CG. And now you're going to intersect omega not with K, but with K plus a little bit. Okay, you add a little bit. So the question is, does omega intersected with K plus little r b shrinks? And I claim that it does. You see in this picture, if r is very tiny,
In terms of diameter, right?
let's say shrink
diameter.
right now in terms of volume, just to. In the end, you don't want volume, but yeah.
But then it doesn't, right? So for a ball.
Exactly. So the problem is going to be really the width of omega. So you see in this picture, if little r is very tiny compared to the width of omega, then of course it's going to shrink in every senses. So here is the lemma.
But what is r? I guess the question is what is r here, right? So because like.
R is some small constant.
But is it comparable with diameter of omega?
Diameter, yes, but it's not about diameter because think, you know.
I mean, okay, take a ball and.
Like take this
Then.
and cut it like that. You know, the volume is going down, but the diameter is not going down.
Yeah, but again, sorry, simple example. If you take a ball, just cut it in the middle and have this like tiny stripe, it would contain like substantial fraction of everything, right?
Right.
That's okay for us. As soon as it is like less than 90%. Okay.
Yes,
okay.
exactly. You just need to reduce by, you know,
Sure.
0.1. So the lemma is just if the mean width, you know, and whatever the precise definition doesn't matter, of omega is at least, let's say, 10 d squared times little r, then the volume of omega intersected with k plus rb, this is going down. This is smaller than 0.9 times the volume of omega. Okay, where and you assume that k does not contain the CG of omega. Okay, so basically this you can think of it as a fuzzy cut. You know, a precise cut would cut through the CG. Here it's fuzzy by this little r, and fuzzy cuts are fine provided that the mean width is small.
Sir,
It's
don't
not
think
too small.
I read your handwriting. So do you
Yeah.
mean the big R over little r is larger than or equal to d squared?
I mean, big
So,
R,
could you read it for me?
little r
for
times
for
b.
the, for the lemma, the assumption.
are each the mean width of omega, the smallest width. You look at in all direction. Yeah. If basically if it contains a small ball of size at least this, then you're good.
This is d squared times a little r.
Yes. Sorry. Yes. And you see, if you keep reducing the volume and the mean width does not get too small, then in fact at the end you're going to get something small. Okay, so provided that the mean width does not get small, you're good. The problem is what happens when the width gets small. Okay, so the only problem left, and I will conclude with that, and this is in a sense, this was the only problem all along, but so imagine I keep cutting like this, and eventually I get to this thing. This is my set omega. Imagine this is omega. Okay, so now the trouble is I might move to the CG, but I keep shrinking like this. So it never gets enclosed in a small ball. And I keep moving because, I'm moving to the CG of omega, but I have this k plus little r. So every time I move a little r. So the key trick, let's assume we're in dimension 2. And this is really the picture of what's happening. CG is here. So the idea is to then play recursively by induction on this small interval, on this small segment. You just play here. Now you're getting sets. If at some point you cannot satisfy things in this set, then you have cut off the large direction. So you make progress on the large direction. What could happen is that it's always possible to satisfy the request by staying in here. So the key difficulty, and people knew this in online algorithm, is something like this. What if, so these are different requests that I'm drawing. So there is one common point which is not paying anything. And the requests, they keep being this, one-dimensional line that intersect like this. If I'm being myopic and I'm playing here, I keep moving like that. I keep moving, whereas opt could be sitting here, or maybe opt is even further away. Opt is not paying anything, and I'm very dumb. So the key trick is to say that if this happens, then in fact I know that opt cannot be, maybe it cannot be there. There is some point that I can cut along the long direction. So then I get a cut along the long direction, and I make progress on the long direction. So the key, let me just write this. So the key is going to be you decompose, you have V set of small directions, and V perp, the long direction, and the potential, the new potential that you look at is the volume of the projection of your set omega on the long direction. Okay, so you look at the things on the long direction, and if this becomes small, since it's long directions, you're included in something small. And the key trick is here, I was telling you, in one dimension, in a two-dimensional space, it's very easy. You just keep following the request until you cannot, or until you have moved too much. But if you're in higher dimension, let's say I'm in dimension 10, and right now I have 5 small dimensions. So I have a 5-dimensional small problem in this 10-dimensional thing. What do I do? And the idea is just to use, by induction, to construct those things and to say, I have a 5-dimensional selector. So I'm just going to use the 5-dimensional selector here until I make too much movement, and then I can certify that opt couldn't be there, and I get a cut along V perp. Okay, so this last part is in fact the key part, but and I can explain to you more after. But let me stop here for the main thing. Yeah. Okay, is there a question or something on
so
this?
So you call it ellipsoid method, but there are no ellipsoids here. It's like balls.
Well, thing is, I called it ellipsoid. You can really think, it's true. It's more like center of gravity method. Yeah, it's
so
not really
I
ellipsoid.
have one question. So
Yeah.
So how did this seems to be kind of like high-level thing they also did for like nested convex bodies. So
Sure.
where is the difference between these two problems? Like,
It's there. So, so the difference is here. So for nested, the key thing is that for nested, you can just wait here in this low-dimensional thing until just the sets do not include this anymore. And when it does not include, at some point you have the set shrinking. As long as the set has some intersection here, you can just be there. And at some point it will have no intersection, and then that's it. You have cut along those big directions. in this non-nested case, this never happens. It could be that the set, they always intersect. You can always move there. You feel like you're doing great, you keep satisfying those requests in this little thing. But in fact, you're doing terrible because there was a point over there who was really paying nothing. So the point is, here you really have to do something very subtle to combine all of the information you have seen to say, aha, I'm moving that much. It means that opt cannot be here if it's not paying much. So let's go over there. Yeah, so this is really, the key difference is in fact here.
Is there a part 2 of this talk? Or?
We can do a part 2 later, yes. We can do a part 2.
So where does the 2 to the d come from?
The 2 to the d comes from exactly here. What happens is, imagine your competitive ratio is omega d. Okay. So what happens is here, I was telling you in this lower dimensional thing, you wait until you have moved a lot. What is a lot? It's more than the competitive ratio. So what happens is that you do the competitive ratio, you will do the one-dimensional thing, you will do the two-dimensional thing, etc. up to wd minus 1, and you have some extra cost plus d, so you get something like that. That your competitive ratio is basically the sum of the competitive ratio in the smaller dimension plus the last one. And this is exponential.
And for your method, this is necessary, this exponential loss. So there is an example where...
Well, yeah, I mean, the key point is you would like not to recurse through all the dimension, but we don't know how to do that.
But you also don't have an example which shows that.
No, that was... So right now, as far as we know, again, this online thing could be as easy as a classical offline.
No, not for problem in general, for your method. So you can...
But what does it mean? A method is... So, okay, here I told you a concrete method. This concrete method is exponential.
Okay, that's what I'm asking.
This concrete method is exponential. But maybe there is a slight variant where you reuse information much more smartly between the different dimensions. But that's a great problem. We don't know. Okay, let's end here. Thanks.